and some isn't because it is very expensive. So if you're starting out in this field and you've been doing some computer simulation this week, you can do computer simulation of circuits, systems, chips, transistors even, any level. And using simulation, it can estimate very quickly, if you do the simulation correctly, where any fault might occur. It could be a design fault, or it could be an environmental fault due to overheating or something else. So, and with simulation we do, you may not know it, but I don't want to go into it today. You could do a whole course on finite element. Finite element simulation is a sort of point-by-point simulation. You digitize the system. You set up all the parameters for materials, material sets for, say, copper for a circuit board, solder for a solder joint. Put all these into the system. One we use is called ANSYS, like a world-class system. Once you've fed all the equations in, put all the equations in for whatever you're doing, heat analysis or vibration, and then do a simulation. Hopefully it'll produce some discrete points to show you how the thing behaves. But I mean, it's very complicated. So we had one student, you'll see his results as we go through. But it's like learning any CAD tool. Once you learn how to use this simulator, it's very powerful. And it's a good first attempt. Once you've got the simulator to work, it can help inform the real testing. So I'm lucky enough to have been in an industrial validation lab in Europe. You want to try this? It's good. Hello. 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 This type of microphones. Is it working? Hello. That's it. Yeah, we got it. This guy used to work for the Beatles. He knows how to fix all the problems. Okay, so if you're going to do industrial scale validation testing, remember I said it might cost £250,000 in English money to test a circuit board. So you can be pretty confident it's going to work in a vehicle. So you need the expensive test equipment, you need to train the staff. Even if you cook it in an oven, you need to learn how the oven works, and so on. And machine time is expensive. If you've got a machine that costs £100,000, £500,000, just for the fact the machine's sitting in your factory, it's costing you money. Depreciation. And it's got to be a specialist centre. There's not very many generalist centres. If you go, ones I know in Europe, you've got EMC test centres, they're specialists for testing EMC testing. I also have my own EMC chamber. Actually, I've done a lot of testing for companies, almost free of charge to help them see if there's any fault with their products. The validation lab, though, you need different types of equipment. And you might be quick at designing circuits. Doesn't matter if it's a chip, a circuit board, or a whole system. Say you think, oh, I can design that in 2 weeks. But to do a validation testing might take 2 months. So if your boss says, when can we release this product, you have to factor in design time, test time, and validation time, which a lot of people, when you're starting out, wouldn't know to do. If you launch it without validating the products, it can be done, but it's risky. So just a few snaps I've got off the internet of different ovens which I've seen, different equipment. This is a Thermotron oven used in the company I work with, and basically it's for different sizes. It goes from a small, what we call a pizza oven, where it's the size of a sort of 12-inch, medium-sized pizza. You can put the circuit board in different directions. But it's not just an oven. Round the back, you have a connection panel, so you can test the circuit hot and cold while it's actually working. So you'll drive the circuit in its normal operation with input signals, and you have a load bank. Say it's a car, it might be driving petrol injectors, so it'll have a bank that looks like a petrol injector. I'll carry on because otherwise we won't finish. So inside this chamber, this is a smallish one. You could get big. It's working again. They can hear. It's okay. So inside the chamber, you go from say 0 to 70 degrees, normal operation temperature. But the ones for automotive will go from say minus 40 to plus 150. That's the range. So it means we need heating in there, but also cooling. So you need a cooling sort of plant. And you saw the curves we had yesterday. You go, say, plus 130 to minus 40 very quickly. So this changeover is quite important. There's two things you do. You do gradual changeover, or you might do thermal shock. Gradual changeover is where you put it in at high temperature, drop it in a basket to the bottom, and it immediately goes to from, say, plus 125 to minus 40. Or you might do thermal shock, where the basket just drops down. It's different sorts of tests. You also do drop testing, which I didn't mention really. You get your phone, you drop it. We have drop tests, and actually have things like ball bearings hitting, say you want to test this, might have a ball bearing or some weight hitting this to make sure it won't break. Because you're going to... This is the one I like the best, because this is the newest one we're working on. This, I got an Indian lady, a PhD student from Assam. I managed to contact her yesterday, and she's at the moment doing vibration testing in the company. And these vibration shakers are very big. So from a washing machine side, if you know a standard washing machine, upwards. And that means they're very expensive. That's inside there, you've got a big coil and sort of a piston like a motor, and you can vibrate it at frequencies from, say, a few hertz up to, say, a few kilohertz. So how you work it is you put a block on the top, a test block, maybe aluminium, you put your circuit boards in the test block, and again you can power your board if you want to while you're vibrating it, or you may just want to vibrate it and see what happens to the solder joints, which is what we're doing. On top of this, over here, on the big ones, you have sometimes a thermal chamber that drops down like a big oven on top of this. So you can do vibration and temperature cycling at the same time. We call it mixed environmental testing. And if you've got enough equipment, you can spray water at it as well. But that'd be quite difficult because you don't want the water to go into this machinery. So this is vibration in one plane. Most of these shakers, you can rotate it 90 degrees. You have a big table. Usually it's made of slate or some heavy stone. That goes in that direction, call it a slip table. So you can vibrate up and down or both ways because you have to consider all the different axes. So how it works in practice is you have a vibration profile based on where the product's going. So vibration profile for automotive will be different from, say, consumer electronics. And obviously you want to test it with testing, so you've got an aggressive profile. So a lot of experience is required to do this sort of testing. So once you've done the testing, you want to... We did talk about acoustic microimaging, sometimes called SAM. And there's an instrument, acoustic microimaging system. This system is about $200,000 to $300,000, so it's not cheap. But it can penetrate through penetrate through the chips and examine solder joints, which is what we're using for it very effectively. Very good for finding delamination when layers separate, because it's very good for finding cracks. So when you've got cracks, you have an air gap, and it reflects the signal back. It's very nice to have this in your lab. So there's yours truly, sitting in the lab, having negotiated a very nice price from a company, because being a university we can buy X-Demo. And we have a very good relationship with the company Sonoscan, which is an American company, but they have a sales office in the UK. So there's the scanning system there. Inside there is a water tank, and then we have a head we can put different sensors in, and it moves in raster fashion, very mechanically based, up and down, but very accurate. The scanning in X and Y is probably better than 1 micron, so very accurate. So we get 2 screens. We have a scan screen and a processing screen, and we've actually developed our own toolbox to do the image processing, which I'm not talking about this week. But the trick is, again, this is hard to use. You need to learn how to set up the transducers, where to focus the transducers, temperature of water is important. If you go to the high frequencies, you may not know, but acoustics in water, there's less impedance in water as you heat the water up. So sometimes we heat the water up to 30 or 40 degrees C, which is warm in the UK. Maybe you don't need to heat it, but normally water's sitting about 10 to 15 degrees C. So we've also got an X-ray machine, but I didn't ruin this one with my mugshot. We've got one similar to this called the Tiger. And inside this chamber, you've got about 24-inch by 24-inch platform, so we can scan very large boards. And the platform again moves in X and Y, so this chamber is quite big in the X and Y direction. And the X-ray machines down here, sending the X-rays up and in the top. You have a hemispherical head, so you can swing around. You can take X-rays from different angles, which is quite good for looking at shape. So rather than a 2D planar X-ray, which is the sort of thing you might do in basic hospitals, for looking at bones and so on, we can swing it around and see if there's anything from a different angle. When we bought this, it's probably 10 years ago, this was about £150,000. And the accuracy is supposed to be 1 micron, so pretty good for X-ray. Right, if you've got even more money, if you're working for a big company or you're a big research unit, you might want one of these. It's a 3D X-ray tomography system. These are about £1 million. Very complex. So I did say the other time, it might take 12 hours to do the scanning and reconfigure the image, but these get a voxel size. If you know what a voxel is, if you've got a pixel on your phone this size, a voxel, if you can draw it, is the cubic volume. And these sort of machines, I was checking last night, the voxel size is about 50 nanometers. So very small, so you can see defects in solder joints very well. The trouble is it does take 12 hours to get the picture. And if you want to do a circuit board, you can't fit a whole circuit board into a chamber of the highest resolution. You have to cut it. You can only do 50 nanometers on a small sample, say maybe as big as your thumbnail. If you want to do a bigger sample, the resolution's not as good. So there's drawbacks in all these things, so it's a bit of know-how how to use it. Standard, this is just a picture I found, but scanning electron microscope has been used for many years. It's got very high accuracy, as you can see there, in the nanometer range, for looking at any objects, using biology, engineering, and so on. Most universities and most actually companies now doing validation will have one of these, or maybe two, because you can not just look at the microscope side, you can look at the materials by introducing X-ray analysis into these things. And again, they're not so easy to use. You need an experienced operator or a technician to help you. We've got them at my own university. We've got maybe 3 or 4 different SEMs, but we have a guy full-time who's working them. So the key is, really, we need to do non-destructive testing when you're doing product analysis. So there's a list of the things we've talked about. There are a few new ones. Optical imaging is also good to look at the top of objects or for missing objects, but it can't look at hidden objects. This 3D X-ray is the future, I think, for hidden objects. Some things were being investigated in my own group, resistance and conduction measurements across the joints as they degrade. If they're starting to crack, resistance will go up. Then we can probably predict when they start to crack, when the crack's fully formed. But it's really difficult to find the point where they start to crack. So you have a curve like that, the resistance is very low, and it starts to crack on the heel, then the graph just goes straight up. Really you want it to go steady. So you can see, okay, it's going up. At that point, we know, take that circuit board out of a system, it's going to break, but it just goes onto a heel and very quickly it goes up. So I had some thoughts actually with the Indian lady working for me, but we probably haven't got time in her PhD to look at this TDR, time domain reflectometry. You need very fast circuits, like asynchronous circuits, to find it. What you will do, we use it for finding faults in cables. You send the pulse down a line, it could be a cable, it could be a circuit board, it could be a chip. You send the pulse down, then you see how long it is to get back. So if you know the send and receive time, which will be very short because it's speed of light stuff, if it comes back a bit quicker, you know there's a break in the circuit because it's reflected from a discontinuity. So this is another thing that's just starting to develop. But I mean, I had a bright spot in the middle, and the dark ring on the outside. And as the solder joint starts to break, this gets brighter. And the standard test we did with our initial work is we're looking for how the intensity grows. As the crack gets bigger, the reflection gets bigger. Okay, so this work is done. This is the team, although Ryan, who you saw yesterday, was also involved at this stage. And this is a PhD student. His name is Chan Li. He calls himself Bali. He's a Chinese Malaysian. He's the only Chinese Malaysian who used to have ringlets with tin foil in his hair. But he did the FE simulation. He was one of our master students who stayed to do a PhD. And I'm delighted to say he's gone back to Malaysia and he got a job with Intel. So it's good for us that our students are going to good places. So he's in the validation lab in Penang with Intel for the last 2 years. And we're still in touch. And he's made his hair, because he's in industry now, his hair is different. But he's an interesting character, this guy. Guanming Zhang, again, he's my reader. So he's an expert in ultrasound. He's coming from electronics engineering background. And I'm an electronics engineer as well. So, and we have some interesting discussions on the way. So first of all, I'll just reflect what we did yesterday, acoustic microscopy of packages, and what's the objective of the project. It's all about modelling in this case. We wanted to know, could you use the techniques? He actually discussed it with, we proposed jointly, it's like a joint development, and how could we actually help this to analyze the solder joints better. So here's a couple of joints. These are all taken in our lab. This is from our X-ray machine. These are solder joints here. This is from the acoustic microimaging machine. Unfortunately, we're not quite on the same scale. So in the X-ray machine, you're looking for solder boils that have reflowed and there should be a certain shape. X-ray, you can see, it's quite detailed. This is sort of 1 micron resolution. You can see these, that one in particular, is slightly different shape to some of these. Look a bit more like the head on an old-fashioned match. So there's some faults there. And there you can see the bright points. This is where the joints have cracked or nearly cracked. So these should be more or less the same. So why do we use ultrasound or acoustic microscopy? Well, it's non-destructive, very sensitive to delamination and cracks, and it can detect sub-micron discontinuities very well. But you've got to set up various things which we'll look into as we go through. Very frequency dependent. The higher the frequency, we go up to about 1 gigahertz now, but on our equipment we can go up to 400 megahertz. The higher the frequency, the better the resolution, but you don't get something for nothing, the lower the penetration. So if you've got high frequency, you can't penetrate through the product. Whereas you go down to, say, 10 megahertz, you can penetrate through the product a lot deeper, but you can't get the resolution. So there's a solution for you. It's a difficult one.
AMI is able to detect the hidden defects also?
Yes, all these are hidden under the joint. They're all hidden. Yeah. Here's a picture. This is our flip chip I've been talking about yesterday. 109 joints. This is looking through the top of a chip. So we've got the top of a chip which just like a shine. It's a flip chip. Yeah. Flip chip like a shiny silicon surface. 109 solder balls underneath. So we go through the top and can detect the joints underneath and anything. And we can penetrate down at some point, all the sound is reflected, so you can't penetrate any deeper. So this is a problem. As the frequency goes up, you can't penetrate as deeply. It gets dispersed through all the different things. So this is the thing we're looking at. So we decided, why is it like this? Why is it like a donut? Really, we'd just like to see the bright spot. We don't want to see this dark spot around the outside. Because it's curved, the solder ball, we think, it's our proposition, the energy is dispersed around the curved side. really we just want to see a black and white picture, and the white picture to come out. It's like a grayscale and this donut shape. So we had the idea, and it's proposed mainly by the student, why don't we use the dark, which is the area, is a bit of lateral thinking, why don't you use as well as the bright spot to try and detect the failure? And guess what, it works. It's nothing like an idea that works. And I don't think it's been done anywhere else when we did it. So we're still developing it. So we wanted to simulate it, and then we did experimental results to prove it. So here's the idea. We got a chip and a solder ball, and we do all this testing underwater to couple the ultrasound. So water gets in. We don't want any air bubbles. Air bubbles will reflect the ultrasound and give us a false result. So we have a squeezer. We might go around with a little water squeezer, get all the air bubbles out from everywhere. It's in the water. And we'd expect some reflection from this point as well as where the chip meets the solder point. It's reflected very well at discontinuities due to the change in acoustic impedance. Higher the change, bigger the reflection. So it's scattered due to the edges, but we thought, well, there's something going on around here that we can't really understand experimentally. So we did the simulation first, and then we did the experiment to see if the simulation was correct, which is the best way to do it. You could do it the other way around as well. But. So here's the experiment that came up. If you're doing modelling, you've got to come up with, well, you've seen in my lab, if you're doing it, doesn't matter if it's a circuit board or a transistor, you've got to set the boundaries and what you're going to start with. So if the transducer on the scale here would be way up here. He started out with a transducer up here, and he kept doing simulations, and even after 1 week he didn't get any answer. Then we realised, because the points are too big in this final map, we have to move the transducer closer down to the solder. So he made a virtual transducer, and then this gap is smaller, because every point there has to be simulated. There's a finite element step through. It takes millions of operations. So he set up this virtual transducer, tested that, and finally applied it to the solder bump. So it comes through the silicon die. As I said, the silicon die is a flip chip. Then there's underbump metallization, aluminium, nickel and copper, I think, before you attach the solder joints. It's got to go through those layers as well. So all these factors have to be entered in. There's a solder bump. R70 means it's 140 microns diameter. And there's the water. And we're ready to go. So it's using ANSYS, and a lot of very steep learning curves to use ANSYS. He's using ANSYS at like what I call machine code level, not using any blocks. And he struggled a bit. After 2 years, he got some really good results. Because he worked at it. If you work at anything, you will do well. So here's something, because it's a symmetrical problem, the same with any signal processing, we only do half of it. That saves half the time straight away. So that's a good point. So we're just simulating this side, and then we can just reflect the other side, because it should be the same in this. So he's scanning half a bump, so half of model, and he's iterating it at half micron or 500 nanometer scale. So this is the sort of picture he gets at the start. Yesterday, if you were here, you saw we had an A-scan. A-scan is like the oscilloscope trace, comes out of a transducer. At every change in material, you'll get this type of pulse. And depending on the size of it, this is quite a big one, these are smaller ones. There might be something there, it could be nothing really much there. Changing of a changeover, you'll get a bigger signal. So once you get all these A-scans together, you join them together in a slice through material. It's a virtual slice, you don't have to cut it. You get what you call the B-scan, which is this one. So A-scan is a single trace, B-scan is like a slice. So you can decide you're going to slice it like slicing bread, but virtual slices. You keep the bread intact. So you slice it through, and you get this B-scan. So these bright, bigger peaks are brighter, the dark areas are dark. Okay? So this is quite neat, and you can see there's some change there going on. And this is where we're interested. This isn't just a straight line with some curves So it's the silicon to bump interface. So when we do ultrasound, we normally set a gate, because you've got this A scan, so you'll set the gate. Say you're interested in this layer here, say that's the reflection there, you'll set the gate somewhere to capture that pulse. You might capture all of it, or you might just capture part of it. And that then focuses on the. And if you do that, you get what's called a C scan. There's a lot of ABCs in this. C scan's a planar scan, as we'll see later. So he sets the gate. The gate's this big. As you would, this is a virtual gate simulation. Sets the gate. So anything for the highest value in the x-plane, and then he plots it like this, and he gets this type of picture. So the idea was there's some edge effect going on around here, and you can see it dips when it comes up. We would think it'd just go flat, then go up. We wouldn't expect it to dip. So when we have to display the data, so the student himself came up with a novel way to display data called this. Instead of a C scan, he called it a C line. So he took a line through his data, which is on this graph. He decides where the line is, and then he plots it just from the radius to the circumference, and then just as to produce this donut, just goes all the way around, and whatever's on that line, he just replicates to make a circle. Then we compared it with a real scan to see if it's similar. Okay, the scales aren't the same. We can see the basic idea matches. So this was quite a good idea. And we published this work in a couple of different journals, and it was quite well received. You know, good high-profile stuff. So trying to think about exactly what's happening. You've got the pulse curve from here. Some ultrasound is reflected, which is what you want. You want it reflected back in the transducer. If it's a low level or a high level, you want to capture all information. But around this curve and this edge, the signal's been scattered, so probably not so much signal gets to there. So we're saying the edge effect, which should appear on the edge, is actually occurring somewhere else. And at the moment we didn't know where it was. So the edge effect occurs before the pulse nears the beginning of the edge. There's something scattering off there. And there's the spot. So if the spot size is 5 micrometers, around there, we don't know where it's penetrating through. Because this edge is filled with water here, with a high impedance mismatch, we expected a big signal, but the signal's going darker. So why is that? Here's some pictures. So here's, after 2 years and maybe a bit more, hard work and answers, you might get some simulation results. So there's just one. I've got a whole load of these, which, so the ultrasound pulse comes from the top there. Red is high intensity, and it goes down, that's the peak, going down to the light blue, which is the lower intensity. So most of the signal's there, but you've got a side lobe there and a side lobe there. And there's a solder joint edge. You expect that side lobe to continue down into there. On the simulation, it seems to stop around about there. So if it stops, it means no energy is being reflected back. So you're going to have this dark ring, which is what happens in reality. So saying the side lobe should like to reflect strongly from the water interface back into the transducer, but it shows a decline there. You should expect that to be, say, green around there, for example. So what happens in reality? Well, what we're trying to look for is when the solder joint degrades. So there's a good one in the left-hand column and a broken joint or a cracked joint in the right-hand column, as you can see the difference. What we're trying to do in our latest experiments is try and find out where the first crack starts to initiate. So not joint, microns or 120 microns. To do it. So there's the transducer again. So we're seeing that. And here's what it gets when it converts that into the CAD file. It's similar colours to your TCAD. Maybe these CAD people use the same. The colours, each one means a different material. So there's the silicon, there's the solder, and the idea with Stuart Hardy is going to put a crack in. I think the battery's gone. Anyway, we'll put a crack in at 25 micrometers and extend the crack halfway across the joint, 75 micrometers, and increment in 2.5 micrometers each time. Each time he does it, he iterates his whole finite element program that might take a few hours to run, get some results. So then from his results he gets this automated or simulated B-scan now, similar to what we get from a machine. And you can see it looks similar to the initial real one. But what I discovered was the dip, due to the edge effect, you can find from that trace by gating out the B-scan between, in this case, 43 to 55 nanoseconds. You can try and find out, and he calls that cap X. Cap X means like a cricket cap. You put it on your head, as your head gets bigger, the intended dip Y is how low this edge effect dip goes down. So we're looking for change. You can see one changes up, one changes down as the air gap extends, which is what you expect. So it seems to work. So then we got some real images. This is 32 cycles of a thermal cycling test. So naught is a good joint, and by 32 cycles it's just about cracked because it's getting very bright. But you can see the dark area is also changing, getting smaller. So if something's changing, getting bigger or smaller, you can use that for failure detection. And again, the signal's quite noisy, but you can still use it. Then we got a proper C-scan image. The C-scan image is the planar image taken from a microscope. And he took two plots in the X-plane and the Y-plane and plotted them on there. You can see he got a similar shape to what he got from his simulation. It's like a sort of peak in the middle and two side lobes. So when he did his C-line plots, it looked a bit of a mess, because you can't see so much about data, but then he changed the triggering point, and look at that. The important thing here is triggering points, but as you go from 0 cycles, 8 cycles, 16, 24, 32, you can see there's a change on that. Well, you could say it's the values starting down there, each cycle is creeping up. At the same time, this gap is growing. The bright spot is growing. This is the donut around the bright spot creeping up. And after 32 cycles, the joint's either broken, in most cases, or on the way to cracking. So then, just as a sort of proof of concept, we got the experimental data, which is the thermal cycling. You can see we think it starts to crack just about there, around about 12 cycles, and by about 24, definitely by 32, this has gone up. There's a good chance it's broken. On this one, the simulated data, this is the width of the air gap, and the same point as the width of the air gap goes. This is saying really that by the time the width of the air gap has gone up to there, this is corresponding to this, which shows that it should have broken. So the cap X, which is the size of this central point, again, this is on the real data, experimental data, from 8 cycles up to about 24 and 32 with a large rise, which meant the cap's growing. And on the simulated data, it's a bit noisy, so he's drawn a best the best fit on the curve. But you can see it's going in more. So for the first study, it's pretty good. So I've gone quicker than I thought, but we've finished. So just to conclude, ultrasound image of a spherical solder ball exhibit this edge effect. Okay, so if you think of a ball soldered on the top, you've got things are coming off which you want. You can't predict what's happening there in general. So we've developed, or the students developed, a novel C-line plot, which is a new way to get the information out of the experiments. And then he's used this with his two measures, the cap measure and the dip measure, which is the donut, the black donut. Through his simulation, the idea could be seen that you can characterize solder joint failing. Okay, so then we did the experiments, which were done in parallel with Ryan, the other student. We did the experiments together. And it's nice that the experiment results confirmed what we found. So this was applied to this flip chip, 109 solder joints of about 140 micron, but with the right machinery you could apply it to any product. Same technique if you're soldering products. Solder joints now I've seen down to 40 microns or less. And then what about if you get a nano particle, 5 to 10 microns of the solder ball? That could be the future, if you can make it. The trouble is, how do you make these things get smaller? And that's for you to do, not me. I'm too old now. So you need to be quite an expert. I'm not an expert on doing that. I think I can see, like you say, the problems. So the solder joint goes from, say, 100 microns, 40 microns now, maybe less, say 20 microns. How do you cut it effectively, even with a laser? Margin for error is very small. And if you want to cut, if there's multiple die inside the chip, how do you cut inside the chip? Actually, we can actually look inside the chip. One thing we do is called die etching. Have you heard of this? So you want to look inside the chip, and it's a plastic package. You put the package down and use some maybe acid, and you can burn off the top of the package rather than using mechanical. Mechanical force is what you're talking about. So you burn off the top, and maybe you can look in first with an optical microscope, and maybe even probe electrically inside. A lot of these, I've only touched, this is only one technique, really, the ultrasound. There's many more things you can do. Other people use iron beam, milling use iron beams to burn layers away and look at what's underneath. Very delicate, at the chip level, it can be really... If you want to go into this, you spend your whole career looking at one technique, probably, if you're that interested. But you're all going to be chip designers. You'll be designing what you want to design. So I just want to say before we finish, this is the last lecture I've got. Then, unfortunately, you've got, after the tea break, you've got the test. And then I think you've got the last lecture from the course organizer. And then after lunch, we've got this valedictory function. And I'm delighted that you've all attended. I'm delighted to be here. As I first came to this place about 22 years ago. And I know it's a good institute. And I know moving around is just the same. The chaos on the gate. So once you get from the other side of the road to here, it's very nice. And thank you for your attention, and I hope you all do well in your future careers. And but don't forget to think widely. And then as you focus down, and take advice from people. It's nice to work on your own to solve a problem, but working with a team, sometimes you get different ideas. So this PhD student was a bit left field. For 2 years, he was struggling to get the stuff working, but with support and working together, and a nice atmosphere, you've got to be relaxed. You produce some very good results. And I never envisaged he'd get a job with Intel, but because he can take his thesis and show the work he's done, and he's a lively guy. He's got a nice job, And I'm delighted for him, because this is why, if you take any student, you want the student to get a job that's suitable. You know, and the same for you. You don't know the opportunities. It's a world out there. Tell all about. The jobs are everywhere, and the opportunities, you're young, are anywhere. So you can decide now on to roadmap your own career. You could want to stay in a while, but do a master's here. If you're not doing a master's, a PhD, you might be lucky enough to get faculty here, and that's great. That's what I did. That in my university, I got a degree, a PhD. Then I went to work 2 companies before I came back, so I got some industrial experience before I do the teaching. Then you can say, well, actually, I designed this, and it's different design in industry to in a university. And my degree course was sandwich. So I went every 6 months, I went to a different industry. So I went to the steel industry. So I'm from a steel town. Sheffield makes very good stainless steel. So I've seen the danger in steel factories. It's a lot more dangerous than electronics. I liked it, it's good, but I thought that's not where I want to work. It was a good decision, because steel industry in the UK has gone right down. The different places making the steel now, so. And things will change. Don't just say, I'm going to be a chip designer. In your career, you might change direction 2 or 3 times. You're only young, I say electronics might start to disappear and something else might come up. But the skills you've got in thinking and designing will take you to the next step. And don't get married too young. Okay, well, I think I'll have a break there. It's a bit early, but I think the tea is being served at what, 11? What time is it? Is it ready? Well, we'll take a break. If it's not ready, we can just stretch your legs for 10 minutes. Okay. It's finished now, it's finished. Yeah, we've gone very fast. Teak high.